Okay, now that we know about entropy and how it factors into the spontaneity of a reaction, we need to bring back our friend enthalpy and also talk about that. Now it's time to do that comparison. So enthalpy, some reminders from that. Remember, changes in enthalpy we designate as a delta H. And if it was a positive value, we've called that being endothermic. If it was a negative value, we called that being exothermic. Remember also for enthalpy, things that tend to release energy or things that are exothermic are going to be spontaneous for us. So if enthalpy has its way, everything exothermic would be spontaneous because it's losing energy. So let's bring it down to a lower energy state, which is preferred in nature. However, it's not the only thing that makes a decision. The second piece of the puzzle is entropy. And entropy, we talk about a positive entropy chain means you're increasing entropy or you get more disorder because entropy is disorder. Negative entropy change is less disorder. So it's opposite for entropy. If you have a positive entropy change, that means you're getting more disorganized, and that's what natural tendency is. So for entropy, the positive value tends to be spontaneous. All right? That works out great when it's an exothermic reaction that becomes disorganized. Okay? Those will always be spontaneous, easy. It also works out great when you have an endothermic reaction that is getting more organized because you have a plus and a minus. Those will always be non-spontaneous. That is the easy ones. What gets tough is what happens when you have an exothermic reaction that is getting less disorder, or you have an endothermic that's getting more disorder. So what happens if both signs are positive or both signs are negative? We need some more work for this, okay? So that's kind of what we're going to get into next is what happens when these two numbers don't agree, and is there a way that we can mathematically get a final say in this, all right? And there is. We use this thing called Gibbs free energy, okay? Gibbs free energy, we're just putting another word in front of free energy, which we started this conversation with. So with Gibbs free energy now, it's still just free energy. So it's that energy available to do work, all right? If we actually want to solve for the total available energy to do work, we have a pretty simple equation for that. So the total available energy to do work is our delta G now. We take the enthalpy change that happens, or the energy change for heat, and we subtract away the entropy change times the temperature, okay? If you recall, entropy has a unit of measure of joules per Kelvin, right? Entropy is tied to temperature, so it's a joule per Kelvin. And if our equation has to end up being just in some sort of energy, we had to somehow factor out the temperature. So because entropy is temperature dependent, remember how if things warm up is more entropy, if things cool down, less entropy, that kind of stuff. That's part of our equation, all right? Temperature must be in kelvins for this to work. Delta H is almost always already in kilojoules, so that makes that really easy. But for your delta S or your entropy, almost always you have to convert that into kilojoules per Kelvin because it'll be represented as joules per Kelvin because it's normally a small number, okay? But when you start multiplying it times hundreds of kelvins, you can see where that number grows in terms of the mathematical power it has in our equations. So that's Gibbs free energy. Now, it might be easy for us to take a look at this through the lens of a table, all right? And in a table, we're going to break it down by enthalpy, entropy, and Gibbs free energy and kind of see will it be spontaneous or not. Let's do the easy ones first. If you have a positive enthalpy change, that means you're endothermic. If you have a negative entropy change, that means that you are becoming less entropy or you're becoming more organized. In this scenario, if we go back to our equation, if delta H is positive and delta S is negative, well, a positive minus a negative will always give us a positive value. So this will always be non-spontaneous. So mathematically, these scenarios can't be spontaneous. If we flip it and come down to the bottom row, if we have an exothermic reaction that's negative and we have something becoming more disorganized or gaining entropy, now we have a negative, okay, minus a positive. Well, a negative minus a positive is always going to be negative, right? Because something minus a positive is going to be a negative. So in that case, we always get negative values. So these reactions will always be spontaneous. It won't matter what the temperature is of these things. In the other two scenarios, that's when we have to start planning about what happens with temperature, because temperature tells us then who's going to dominate or who's going to win this kind of battle. So going up here now, if we have an endothermic reaction that becomes disorganized, right? The entropy is saying, hey, let's make this thing spontaneous. The enthalpy is saying, no, not spontaneous. So that's where it becomes temperature dependent, all right? We can take a look at what's going to happen with this. If we increase the temperature in this scenario, so we increase the T, that means the multiplier for entropy is going up. So as we change temperature, we affect how much entropy really plays a role in this result. It doesn't really change enthalpy at all. So as we increase temperature, this value or the entropy contribution gets bigger and bigger and bigger because we're multiplying by T. So as a result, this starts to dominate. The entropy will start to dominate. So in this case, the warmer you get something, the more likely it is to become spontaneous, and the more spontaneous it becomes as you get closer and closer to that point, okay? If you flip the scenario where you have an exothermic reaction that's becoming more organized, now enthalpy says, yes, make this thing spontaneous. Entropy says, no, not spontaneous, okay? Again, temperature dependent, but now it's the opposite. So here, if you want this thing to be spontaneous, you want to cool it down because you want to minimize this part of the equation as much as you can. So you want your multiplier here to be as small as possible. So you're subtracting a negative becomes really, really tiny, meaning that the enthalpy can dominate this. So in that case, cooling it down would be more likely to make it spontaneous. All right? Now, ultimately, as long as you have the numbers, if you actually had the numerical values to plug into here, you're fine. But this slide is really good for us conceptually because in terms of looking at your data, you know quickly by their sign whether or not something's going to be spontaneous or not, and whether or not you want to warm it up or cool it down to make it spontaneous. All right? In the world of chemistry, sometimes we cool things down because we want the reactions to slow down and stop. Sometimes we warm them up to slow them down or stop them, or vice versa. It can go either way. So let's do a little practice problem, all right? So here's our scenario. We're going to react some baking soda in sulfuric acid. The reaction happens spontaneously at room temperature. We'll call that 25 degrees Celsius, okay? But it's also endothermic, all right? So we have an endothermic reaction that's running spontaneously, which means something about entropy, okay? If it's endothermic, the enthalpy here would say it would not be spontaneous. So in this scenario, it must be warm enough where the entropy that's going to cause this reaction to run is increasing enough to override the endothermic nature here, okay? Baking soda and sulfuric acid is going to break it down to a lot of little things. We're going to create gases. We're going to create solutions. We're going to break things into smaller parts. So we have lots of things that are going on here that would create more entropy, okay? So let's prove it mathematically now. So the entropy change for this reaction is 240 joules per Kelvin. The enthalpy change is 31.8 kilojoules. Again, this is not per Kelvin or per mole. This is just kilojoules for this process in here, all right? So we have our joules per Kelvin and we have our kilojoules. And then, so first thing I'm going to do is I'm going to plug it into my equation. We go back to that. And I'm going to put my enthalpy value in here. I'm going to put my temperature in here in kelvins. And then I'm going to put my entropy value in here, but make sure I convert it to kilojoules first as we do this. All right, so convert this to kilojoules, convert the 25 to kelvins, and then we plug our problem in and solve it. Okay, so do that, and then pause the video and come back. Okay, so if we look at the solution for this now, we have our 31.8 kilojoules. We're going to subtract away the temperature times the entropy, but we need to be in Kelvin, so it's my 273 plus the 25 for kelvins. I've converted this over to kilojoules per Kelvin, so my kelvins will cancel out. If I do that, I'm going to take my 31.8 minus, 298 times this, and I get a negative 39.73 kilojoules, okay? Being that this is a negative value, we know this is spontaneous, all right? So anytime we get a negative G, it is spontaneous, all right? Now in this scenario, we could ask the question, could we make this non-spontaneous? And the answer is yes, we could, all right? Because they both are both positively signed, when they have the same sign, you can make something spontaneous or non-spontaneous by changing the temperature. Again, we go back to our table to look at this, and because they both were positive, all right, we're looking to make it, keep it spontaneous, we want to warm it up. So if you wanted to have this thing to be non-spontaneous, do the opposite effect here, you'd want to cool it down, okay? So you want to get colder and colder and colder, so eventually, when you multiplied this value here, the temperature would get so cold that this would be less than 31.8. So the subtraction here would be less than that, and we'd end up with a positive G value in this case, all right? So that's one of our practice problems. Here's another practice problem that we can work on. I'll let you guys work on this one on your own, or we'll also possibly do it in class. Thank you.